Good morning everybody. We are with the electrolytic conductance, and last time we had seen the Coleridge law and the Coleridge law of independent migration, and then we had seen the different problems depending on the Coleridge law. We also saw the degree of dissociation or degree of ionization, how it is related with the conductivity measurements. We had seen the equation, or rather the definition for alpha. The degree of a dissociation is nothing but a ratio of the equivalent conductance of an electrolyte at particular concentration and the equivalent conductance of the same electrolyte at infinite dilution. So alpha is equal to lambda divided by lambda 0. Now we are going to the application of conductance measurement or the conductivity measurements. So the first application is to find out the ionic product of the water. Now the water, even in the purest form, it shows conductivity. In the purest form, the water, it shows conductivity. It means that water must be weakly ionizing as H plus and OH minus. As it shows the conductance, that means that water must be weakly ionizing at H plus and the OH minus. The dissociation or ionization takes place to a very less extent, and therefore from this reaction, the equilibrium constant for this dissociation reaction we can write as concentration of H plus into concentration of OH minus divided by concentration of the unionized water. This will be the equilibrium constant for this dissociation reaction of the water, and therefore as this ionization takes place to very less extent, very minute, very negligible dissociation takes place, therefore we can say that the concentration of unionized water is almost constant, because a very negligible amount of it get dissociated or ionizes, and therefore this we can take at one more constant. So this is what our equation becomes. The water concentration I have taken on this side, as this is a constant, so we can take it as one more constant, and this K with this small k is called as Kw, which is equal to concentration of H plus into concentration of OH minus, and this Kw is called as the ionization constant for the water, or it is also called as the ionic product of the water, and from the conductivity measurements we can find out the ionic product for the water. See here, this dissociation, for this dissociation reaction, as it ionizes weakly, that means a very negligible fraction of this get dissociated. If we say that at equilibrium, if alpha is the degree of a dissociation of the water, therefore at equilibrium the fraction of these two ions formed will be alpha, and the remaining unionized form of water will be obviously 1 minus alpha. This fraction will be of the water and dissociated water at equilibrium. Now these are the fractions which will be present at the equilibrium. Therefore their concentration at equilibrium, if I consider that C is the concentration of the water taken, therefore the concentration of these molecules or the ions at equilibrium will be, for the undissociated water the concentration will be C into 1 minus alpha. Concentration of this H plus is C alpha, and similarly the concentration of OH minus will also be C alpha. These are the concentrations at equilibrium. Now we want to find ionic product of the water. The ionic product of water is nothing but the product of concentration of H plus and OH minus ion. Therefore, to find out Kw or ionic product, I need to know the value of alpha and C. Correct? If I want to find Kw, आणि जर Kw आपल्याला फाइंड करायचं असेल तर C आणि अल्फाची व्हॅल्यू माहिती पाहिजे, मग आपल्याला Kw काढता येईल. Therefore, we have seen the relation between degree of dissociation and conductivity measurements. We know that alpha is equal to lambda divided by lambda 0. Right? Therefore, to find alpha, we need the values of equivalent conductivity. And therefore, to find the equivalent conductivity, we will first find the resistance. From resistance, we can calculate specific resistance. From that, we can calculate the specific conductance and all. Therefore, the ionic product can be found out from the values of conductivity. Now, first, lambda has to be determined. We know that lambda is equal to Ls into V. This is our formula, right? In terms of volume, the formula for equivalent conductivity water will be equivalent conductivity of water is equal to its specific conductance into the volume of the water taken, right? Now, the value of Ls, that means the specific conductivity of water, the value is 0.58 into 10 to the power minus 7 moles per centimeter. Now, what this is? Mho. Actually, we know that specific conductance, its unit is per ohm per centimeter. Then what is this mho? Actually, this is inverted. Ohm is inverted. MHO, that is mho. And as inverse is taken, so it can be written as mho. Instead of writing per ohm, we can write it as mho. Alright? Okay. So this is the specific conductivity of the water. Now, we want to find V. Now, we know that V is equal to M divided by D, correct? Because D is equal to M divided by V, therefore V is equal to M divided by D. That means the volume of the water is equal to, if we take it in the equivalent weights, therefore the equivalent weight of the water divided by its density. As equivalent conductance. What is equivalent conductance? It is the conductance of an electrolyte when 1 gram equivalent of that electrolyte is present in the solution. Right? 1 gram equivalent of water. That means the equivalent weight of the water molecule. Now, equivalent weight of water molecule is 18.016. That means as we are calculating the equivalent conductance, so we are considering its equivalent weight. The density of the water is 0.9971 gram per ml or gram per centimeter cube. Now, therefore, we can calculate or we can substitute V as M divided by V. So, lambda is equal to 0.58 into 10 to the power minus 7 into, instead of V, I am substituting M divided by D. So, 18.016 divided by 0.9971. So, equivalent conductance comes out to be 1.05 into 10 to the power minus 6 mho per centimeter square. Alright, actually here 1 centimeter cube is nothing but 1 ml. But as equivalent conductivity, here the centimeter unit is, so instead of taking ml, we take the volume in the form of centimeter cube. Alright. So this is what is the equivalent conductivity water. Now if we know lambda 0, we can find out alpha. Now how to find out lambda 0 for water? From the Coleridge law, we can write this as the ionic conductivity of H plus at infinite direction plus ionic conductivity of hydroxyl ions. And if we know these values, we can calculate lambda 0. Now the ionic conductivity of H plus at infinite direction is 349.8 plus the ionic conductivity at infinite dilution of the hydroxyl ion is 198. Therefore, this is 547 mho centimeter square. square. Per centimeter square. This mho is nothing but, wait a minute. Yes, mho centimeter square. This is what is the value for lambda 0. Now we have got both lambda and lambda 0. So we can calculate now alpha. So alpha is equal to, what is our equivalent conductivity for 1 gram equivalent of the water? 1.05 into 10 to the power minus 6 divided by lambda 0, 547.8, and therefore lambda is equal to the value of, not lambda, alpha, 1.9 into 10 to the power minus 9. So this is what is the value now I have. Alpha I have got. Now from the formula of C alpha, I have got alpha. Now to find the concentration. Now how to find the concentration? See, I am wiping it out again, this part. So we have got alpha. Now we want to find C. That is the concentration. Now to find the concentration, we have taken one equivalent of the water, right? If I consider that I take 1 liter of water, alright? 1 liter, or I may say 1000 ml of water. This much of the water I have taken. How much would be the weight of the water? 1000 ml corresponds to how much? See, we know that the density of water is 0.997. We know that D is equal to M divided by V. I know V, I know density. 0.997 is equal to M divided by 1000 ml I have taken. But that's a weight किती येईल किंवा त्याचा mass किती येईल तर 0. Instead of mass I can say weight by volume. So weight of 1000 ml of water is 0.9971 into 1000. So that is 997.1 gram. This is the weight of 1000 ml of the water. I have taken 1000 ml, that means this much gram of the water is present. So how many moles of water are present? How can I calculate that? See, 18.016 grams of water corresponds to 1 molar. Therefore, 997.1 grams of water corresponds to how many moles of water? That we can calculate. Simply what to do? 99, if I consider here x into 18.016 is equal to 1 into 997.1. So x is equal to simply 997.1 divided by 18.016. So this water is 55.34 molar. So we have found the concentration, that means we have found this term C. If I have taken 1000 ml of water, therefore it is 55.34 molar. That means we have found its concentration. Kasa find केले पहा concentration? I will tell you again. We have taken 1000 ml of water. That means 1 liter of water. And the weight of 1000 ml of water is nothing but 997.1 gram. How we can calculate this? From the density, weight and volume relation. Density is equal to weight by volume. We know density, we know volume, therefore we calculate its weight. Then 18.016 grams corresponds to 1 mole of water. Therefore, this much grams corresponds to how many moles that we have calculated. So water is 1 liter of water is 55.34 molar. Now concentration. We know concentration, we must know concentration of both of these ions, and here the concentration of both of these will be exactly same, that is C alpha. So let's calculate it. 55.34 into alpha is 1.9 into 10 to the power minus 9, and this comes out to be 1.05 into 10 to the power minus 7. This is the concentration. Now, therefore, Kw is equal to concentration of H plus into concentration of OH minus. Both of these concentrations are same. That means to calculate this product, 1.05 into 10 to the power minus 7, simply bracket square, and this is equal to 1.10 into 10 to the power minus 14. This is what is the value of ionic product. So from conductivity measurements, we can calculate the ionic product for the water, 1.10 into 10 to the power minus 14. For calculation of this, we have taken the help of Head-Vallier data, that is the specific conductance of water and all, and the Kohlrausch law. Where we use the Kohlrausch law? The Kohlrausch law we use to calculate lambda 0 for the water, correct? So from the Kohlrausch law and the Head-Vallier data, we calculate the ionic product for the water. For calculating the ionic product of water, what we did? We first calculate the degree of a dissociation, and degree of a dissociation is having the relation with equivalent conductivity. Obviously, from the specific conductance, we can calculate the equivalent conductance. So from the conductivity measurements, we can calculate the ionic product of water that we have calculated. Now, the second application of the conductivity measurements is to find out the solubility. The second application is to find out the solubility of spherically soluble salt. Now, what is a spherically soluble salt? The spherically soluble salt is which is having very less solubility in the water. Those are called as the spherically soluble salt. For the spherically soluble salt, we can find out that solubility from the conductivity measurements. Let's see how. Now, for the salt, when we make the solution of this spherically soluble salt, its specific conductivity is the addition of specific conductivity of the salt and the specific conductivity of the water. Because for taking the conductivity measurements, we always use the water as the solvent, and by dissolving this salt, we prepare the solution. So therefore, the specific conductivity of the salt solution is equal to the specific conductivity of the solvent used, that is the water, and the specific conductivity of the salt. Therefore, the specific conductivity of the salt is equal to, obviously, the specific conductivity of the solution minus specific conductivity of the water. Now, to find out the LS of the salt, if we take the relation or equivalent conductivity for the salt will be LS of salt into 1000 divided by C. This will be our relation for the equivalent conductivity of the salt. As actually here we want to find the solubility. That means solubility is nothing but the concentration. Concentration means how? When we dissolve any salt in the water, therefore the spherically soluble salt, as I have told you, that they have very less solubility. So a very less part, a very less fraction of the salt will be dissolving in the water. Most of the part or the fraction of that salt will remain undissolved. Only the dissolved part of that salt is the concentration or the solubility of the salt. What is the solubility of that salt? A dissolved concentration of the salt is nothing but the solubility of that salt. The undissolved part, that doesn't, its concentration is not the solubility. The solubility of the salt is the fraction of the salt which is dissolved in the water. Dissolved in the sense, the fraction which forms the ions in the solution. That means, for the sparingly soluble salt, its a conductivity will be obviously due to the ions formed. And the concentration that we will consider here, that concentration is a concentration of that salt which is responsible to give conductivity to the solution. That means that this concentration is a concentration which is dissolved in the water, and that is nothing but the solubility. That means that for such sparingly soluble salt, if we write a relation for its equivalent conductance, this concentration is nothing but the solubility for that salt. Alright, and therefore to calculate this concentration, we have to consider the conductivity of the salt only, and that's why I have write this relation. The specific conductivity of a salt is equal to the specific conductivity of a solution minus specific conductivity of the water. We can get the Ls from the conductivity measurements. That means we will measure the resistance. From the resistance we can calculate the conductance, and from the conductance you can calculate the specific conductance of the solution. So direct from the conductivity measurements we will get this value and not this. And we want to find the solubility of the salt, and to find the solubility we need to know the Ls of the salt only, not the solution. This we will get from the conductivity measurements. This we know, right? Therefore, so lambda is equal to calculate the solubility of the sparingly soluble salt. I have written this relation. The equivalent conductivity of a salt is equal to the Ls of salt into 1000 divided by C. Now, as solubility फाइंड करायची म्हणजे थोडक्यात आपल्याला कॉन्सन्ट्रेशन फाइंड करायचं. म्हणजे जे काही इक्वेशन आहे हे मी कॉन्सन्ट्रेशन साठी तयार करते पहा. लॅम्बडा Ls of salt into 1000 divided by lambda. This is how the relation will be. And if you know the Ls of salt and lambda, you can calculate the solubility. See now, this we have calculated from the conductivity measurements. हे आपल्याला conductivity measurements वरून काढता येईल. वॉटरचा कंडक्टन्स आपल्याला स्टँडर्ड व्हॅल्यू माहिती आहे. मग याच्यावरून हा आपल्याला याची व्हॅल्यू मिळणार आहे. The specific conductivity of a salt we will get. We will substitute that value here. Now what about lambda? आता लॅम्बडाचं काय करायचं? As I have told you that this salt is a sparingly soluble salt. That means which is having very less solubility in the water. That means here we can write that lambda is equal to lambda 0. That means the equivalent conductivity here is nearly equal to equivalent conductivity at infinite dilution. Why? Because as this salt is a very less soluble, therefore the solution that we have formed is a infinitely dilute solution. Because a very small amount of salt get dissociated or get dissolved in the water, and hence the solution is infinitely dilute solution, and that's why the conductivity of this solution is nothing but the conductivity of the solution at infinite dilution. That means here we can substitute lambda by lambda 0. So Ls of salt divided by 1000 divided by lambda 0. This is what the relation becomes. This value we are going to get. ही व्हॅल्यू आपल्याला मिळणार आहे. मग ही व्हॅल्यू कशी काढायची? ऑब्वियसली जो सॉल्ट आहे, समजा तुमचा जो काही सॉल्ट आहे बेरियम सल्फेट सारखा सॉल्ट, की ज्याची तुम्ही कॉन्सन्ट्रेशन फाइंड करते. ऑब्वियसली बेरियम 2+ आणि सल्फेट 2- यांच्या आयनिक कंडक्टिव्हिटीच्या व्हॅल्यू आपण जे काही आयनिक कंडक्टिव्हिटीचा टेबल आहे त्यांच्या टेबल मधून या व्हॅल्यू घेऊ शकतो आणि लॅम्बडा 0 कसा कॅल्क्युलेट करणार ऑब्वियसली असा या दोन व्हॅल्यूज मिळाल्या की तुम्ही लॅम्बडा 0 काढू शकता एलएची व्हॅल्यू माहिती आहे लॅम्बडा 0 आपण कॅल्क्युलेट केला की आपल्याला काय मिळेल सी मिळेल म्हणजेच कॉन्सन्ट्रेशन मिळेल आणि कॉन्सन्ट्रेशन म्हणजेच स्पेरिकली सोल्युबल सॉल्टची काय आहे सॉल्युबिलिटी आहे सो दिस इज हाऊ वी कॅन फाइंड आउट द सॉल्युबिलिटी ऑफ स्पेरिकली सोल्युबल सॉल्ट द थर्ड मेजरमेंट द थर्ड application is to calculate degree of a dissociation and dissociation constant of weak electrolyte or weak acid or weak electrolyte we can say. From the conductivity measurements we can find out degree of dissociation and dissociation constant for the weak acid or weak bases. How? Obviously we know that alpha is equal to lambda by lambda 0. Correct? Therefore, by preparing a definite concentration of that weak electrolyte we can find out lambda. By this relation we will prepare a particular concentration. So C will be known. From a solution, particular concentrated solution, we can measure its conductance and calculate specific conductance. If these values are known, lambda we can calculate. Correct? Now, lambda 0, according to Kohlrausch law, we can calculate the values. From the Kohlrausch law, we can calculate lambda 0, right? And therefore, we can calculate obviously alpha. So, degree of a dissociation for the weak acid or weak electrolyte can be calculated by preparing a particular concentration and measuring its conductance. So, we can calculate specific conductance and therefore, we can calculate its lambda at particular concentration. Then we can calculate lambda 0 from the table of ionic conductivities. For example, acetic acid is there, which is a weak electrolyte, weak acid. The ionic conductivity of H plus and ionic conductivity of acetate ion we can take from the table of ionic conductivities, and by taking those values we can calculate lambda 0. So by knowing this lambda and lambda 0 we can calculate alpha, and from alpha you can calculate dissociation constant of that acid as C alpha square divided by 1 minus alpha. By using this relation we can calculate dissociation constant. So these were the applications of the conductivity measurements. Now the next point we are moving to is absolute velocities of the ion. Now what are these absolute velocities? Actually the ions, when we compare the equivalent conductivities of the electrolyte, of every electrolyte we take their 1 gram equivalent, and therefore the number of the ions of all the electrolyte, when we take their exactly 1 gram equivalent, all will contain similar number of the ions, right? And therefore total current carried by the ions will be same in every case. See what I have told you. If we take the electrolyte, जेव्हा आपण इक्विव्हॅलेंट कंडक्टिव्हिटी कंपेअर करतो इलेक्ट्रोलाइटशी, इक्विव्हॅलेंट कंडक्टिव्हिटीज आपण कशाला म्हणतो की जेव्हा इलेक्ट्रोलाइटचा बरोबर 1 ग्रॅम इक्विव्हॅलेंट घेतलेला असेल आणि त्याच्यात जेवढे आयन्स असतील तेवढ्या आयनची कंडक्टिव्हिटी म्हणजे इक्विव्हॅलेंट कंडक्टिव्हिटी. मग जेव्हा आपण इक्विव्हॅलेंट कंडक्टिव्हिटी कंपेअर करतो, ऑब्वियसली प्रत्येकाचा जर आपण 1 ग्रॅम इक्विव्हॅलेंट घेतलेला असेल तर त्यांच्यातले जे काही नंबर ऑफ आयन्स आहेत ते सगळे सेम असतील, आणि जर नंबर ऑफ आयन्स सेम असतील तर त्यांनी कॅरी केलेला करंट सुद्धा एक्झॅक्टली सारखा असेल. मग तरी सुद्धा इक्विव्हॅलेंट कंडक्टिव्हिटीची व्हॅल्यू ही इलेक्ट्रोलाइट बदलला की बदलते. मग ती कशामुळे बदलते? तर ही जी कंडक्टिव्हिटी आहे ही कंडक्टिव्हिटी कोणकोणत्या गोष्टींवर अवलंबून असते. द फर्स्ट थिंग, it is depending on obviously the number of ions. The second, the charge carried by the ion, and the third very important thing, that is the velocities of the ions. आता जसं आपण पाहिलं की जर सगळ्यांचेच एक एक इक्विव्हॅलेंट घेतले असतील तर प्रत्येक इलेक्ट्रोलाइटचे नंबर ऑफ आयन्स आणि त्यांनी कॅरी केलेला करंट किंवा चार्ज या दोन गोष्टी तर सगळ्यांच्या सारख्या असतील. मग फरक कशात असणार? फक्त व्हेलॉसिटीज ऑफ दी आयन्स. ऑब्वियसली प्रत्येक इलेक्ट्रोलाइट वाईज त्यांच्यामधले आयन्स बदलत जातात आणि या आयन्सच्या मूव्ह होण्याच्या ज्या काही स्पीड्स आहेत किंवा व्हेलॉसिटीज आहेत त्या वेगवेगळ्या असल्यामुळे प्रत्येक इलेक्ट्रोलाइटची इक्विव्हॅलेंट कंडक्टिव्हिटीची व्हॅल्यू ही वेगवेगळी आहे. सो the equivalent conductivity mainly depends on the velocities with which the ions moves, and these velocities, they are denoted as V plus and V minus. V plus is the velocity of a positive ion or the cation. V minus is velocity of the negative ion or the anion. And these velocities, we are actually not going in the detail of the derivation, but I am directly writing the relation. Lambda is equal to alpha f into V plus divided by E dash plus V minus divided by E dash. This is what is the relation between equivalent conductivity and the speeds or the velocities of the ion. Now, what this E dash is? E dash is nothing but potential drop per centimeter. This is called as potential drop per centimeter. If you go away from the electrode, there is a decrease in the potential, and that decrease in the potential per centimeter is called as the E dash. Potential drop per centimeter it is called as, and this ratio, the velocity of the ion divided by the potential drop, is called as the mu, which is called as the ionic mobility. Mu is called as ionic mobility. This is the ratio of velocity of the ion and the potential drop per centimeter. That is called as the mu, that is the ionic mobility. So this relation becomes lambda is equal to alpha into f into bracket mu plus mu minus. So this is what is the relation between ionic mobility and the equivalent conductivity. See, actual speed and the ionic mobility, these two terms are different. V plus and V minus, these are the actual speed. While what is the ionic mobility? When the velocity is divided by the potential drop per centimeter, the decrease in the potential per centimeter is called as the E dash, and this ratio is called as the ionic mobility. That means lambda is equal to, if I multiply by these terms inside, so this becomes like this, right? And here, according to Coleridge law, we can write it as L plus plus L minus. That means if we compare these two relations, so L plus is equal to alpha f mu plus and L minus is equal to alpha f mu minus. For a strong electrolyte, this relation we consider for strong electrolyte, we know that alpha is equal to 1. Alpha is equal to 1 means the strong electrolytes are always complete dissociating. That means degree of a dissociation for them is 1. Therefore, what this relation will become? Alpha plus is equal to f divided f plus f into mu, or mu plus is equal to L plus divided by f. Similarly, L minus is equal to f into mu minus. Therefore, mu minus is equal to L minus divided by f. These are what are the relation. This relation, if we write at infinite dimension, so this becomes mu lambda 0 is equal to L0 plus plus L0 minus. So this relations become L0 plus is equal to, instead of ionic mobility we can write them as the ionic mobility at infinite dilution, mu 0 plus is equal to L0 plus divided by F. Similarly, mu 0 minus is equal to L0 minus divided by F. So these are the relations. This is the ionic mobilities. These are at infinite dilution. These are at particular concentration. And here these relations we have considered, that is for a strong electrolyte, because their alpha is equal to 1. At a particular concentration, if any other electrolyte is there, so alpha term will become here. That means in that case, mu plus will be equal to L plus divided by alpha F, and mu minus is equal to L minus divided by alpha F. This will be for any electrolyte therefore. This we have considered for a strong electrolyte. Actually we have its a derivation, but we are not going in the derivation part. Just see that the velocities, they are related with lambda, equivalent conductivity, and these velocities, they are considered as ionic mobilities. Instead of considering them as the actual speed, they are considered in terms of ionic mobility. Ionic mobility is nothing but the ratio of actual speed of the ion and the potential drop per centimeter. That ratio is nothing but the ionic mobilities, and the ionic mobilities can be derived or can be determined. And if we compare the ionic mobilities of the ion, it is observed that all the ions except H plus ion, OH minus, H plus and hydroxyl ion, these two ions have exceptionally very high mobility. Otherwise, the other ions, they have nearly same mobilities. Their mobilities are not much different. Alright? Only H plus and OH minus, they have exceptionally very great speeds, and hence their ionic mobilities are also very great. The next concept of transference number. Transference, or it is also called as transport number. Transference or transport number. Now what this is exactly? From the Coleridge law we have seen that every ion migrate independently of its co-ion, and they contribute a definite share to the total equivalent conductivity of that electrolyte, right? That means that every ion contributes to the total conductivity, right? And this total conductivity, the positive ion and negative ion, the share of both of them is added, and we get the total equivalent conductivity for the electrolyte. Therefore, every ion, this transport number that we are talking about, they are related with the speeds of the ions. The transport number or the transference number, they are related with the mobilities or the speeds of the ion, or the contribution in the equivalent conductivity of the ion is depending obviously on the velocities. When the velocities of anion and the cation in the electrolyte are both, therefore their contribution is also same. But when the velocity of cation and anion in the electrolyte are different, therefore their contribution is also different. The fraction of the current carried by a specific ion is called as the transport number. The contribution or a fraction of the current carried by the ion, that may be cation or anion of the electrolyte, that is called as the transference number or a transport number. These transport number, they are denoted as T plus and T minus. Obviously, T plus is the fraction of the current carried by the cation of the electrolyte, while T minus is fraction of the current carried by the anion in the electrolyte, and this T plus and T minus, this always is equal to 1. What this means? This means that T plus and T minus, both of them will be always less than 1. Obviously, the both of them contribution and it will unites to 1. That means individually T plus and T minus will always be less than 1. T plus T minus is always equal to 1. This T plus and T minus, these are nothing but the transport number, and this transport number is nothing but the amount of the fraction of the current carried by a specific ion, that is called as the transport number. And therefore, this, as I have told you, that the amount of the contribution of the ion in the total equivalent conductivity, it depends on their velocities. Therefore, T plus divided by T minus is equal to V plus divided by V minus. This is the dependence of transport numbers on the actual velocities of the ion. T plus divided by T minus is equal to V plus divided by V minus. This is actually the Hittorf's rule, and that we are going to see how it is derived. Alright, next time we will see the Hittorf's rule. This is actually the Hittorf's rule. And generally, to calculate these fractions, T plus and